Today I've got this really cool little, used to be a Compumotor, now it's a Parker CBL161CJ001. This used to be a Copley private label Parker motor. It's got an incremental encoder with commutation tracks for Halls, and it's really small. And I've got it connected to my BEL Copley XLNet Plus drive. I did hook up the earth to the chassis. I'm trying to show a really good grounding here. It's very important to keep feedback signal clean. I've got pin 1 connected to the shield, so the encoder shield is connected to the earth. I have the motor power wires separated from the feedback signal, and 24 volts to power the system. This little motor only takes a few amps, so this 3 amp drive is plenty. This drive actually comes in a 15 amp version. And today I'll be using my new RJ11 to USB adapter, Elastream CBL USB Copley RJ11. And I have the safe torque off connected here, so I should be able to enable the drive and go through some tuning. So I'm just going to show the cabling real quick here. I've got 0 volts and HV for 0 volt return and 24 volt power supply. There's an aux if you have a 24 volt keep alive to keep the actual position alive even if you cut the HV. The motor power wires, we call them UVW. They may call them ABC or whatever. UVW hooks up 2, 3, 4, and pin 1 is frame ground. That's earth. That normally connects the cable shield for the motor power to earth. The motor case gets connected to the frame, thereby connecting the motor case to earth. Normally the frame is earth. We have the feedback connector here. I've got UVW Halls connected, A naught, B naught, X, and hat X. That's index and index naught. And of course, there's plus 5 volts out to the encoder, and a plus 5 volts out, which there's a separate Hall power and encoder power on this motor. And there's signal ground. There may be 2 signal grounds. But most importantly, connect the shield to frame pin 1. And as the case of the drive is also connected to earth at the lug, you'll get a good connection for the shield to earth. Shields must always find a path to earth. So I found the SM series motors here, which looks like the 616CJ, size 16 or 23 is the bigger one, but it's a little motor. They have options for gears and feedback types, and you can even get a little private labeled plate there with your name on it, although this motor is too small to have a plate, so it's just an encoder. But the name tag says Copley CBL on it. But they do lots of customizations, so very smooth motor, no cogging, slotless design. I like it a lot. So I've got CME2 connected over the serial port with my COM device, and it connects and brings up all the parameters. Normally in the beginning you get the basic setup, so you go through what you got: brushless rotary, incremental or digital Halls, incremental encoder on the motor shaft, primary on the feedback device. I'm going to do position mode, can't open over EtherCAT, that's fine. Sinusoidal commutation, buffer the output, that's cool. And normally at the beginning of the day we get the data for the motor. I had an old file from Compumotor, so I just pulled it in. The inertia, I should double check that, but this value gave me good gains. Peak and continuous torque, max theoretical speed, torque constant, back EMF constant. Those look pretty good, so we'll leave that alone. Large inductance, lots of resistance, so some IR drop. So 7 volts per k-RPM, I got 24 volts, maybe I'll get 2, maybe 3, probably not 4,000 RPM. There's some IR drop, so be careful of that. And the motor feedback, 2,000 lines is 8,000 counts in. we can turn on the loss detection. That should be okay. So you enter the data. If you had a break or trying to control the stop, you can enter this information too, but hit calculate, gives you some initial tuning values. And first thing you should do is phase the motor. So I'm going to give it an amp, rotate the current vector forward through 4 electrical cycles, which will be 8 poles. So, and another electrical cycle. There we go. About 8,000 counts. You see everybody gets a chance to deliver currents, Halls decode. Here's the wiring UVW. That was already selected, no offset. The red indicator is slightly leading the black indicator forward and reverse. So it's balanced. Phasing's good. I'm going to go to the I loop. These are the calculated current values. We could compare them. But that came from the torque and the torque constant. And this is the calculated current loop gains. Check out the bandwidth. So this starts at 100 Hertz and steps forward. The motor shaft is not rotating. It's just oscillating back and forth at a high frequency based on the inductance and resistance. 700 Hertz, that's pretty good. We'll take a look at it. We could auto-tune it, maybe get a kilohertz. I'm not going to go crazy fast, so I'm happy with that. Calculated values for the gains. So low VP and VI, a theoretical limit here. Set that to 5,000. I don't think I'm ever, yeah, see, it's warning me. I need some more voltage to get there. Nice tracking window. Probably bring that down to like 30 RPM. And some trajectory limits based on some, peak and continuous torque values and inertia. Those look pretty good. So I'm going to do the tuning. We'll take a quick peek at the current loop. I have a little bit of time here. There it is, commanded and actual. So if the gain was too high, say 2,000, you'd see a little ring or overshoot. So yeah, it's pretty good throughout the pole. Oh, sometimes when you go between a pole, you get a little ring there. So I'm just going to stick with the calculated values. Give me some good current loop bandwidth. And maybe a little bit more interval. So I'm going to wrap up the current loop auto setup, hit start, look at it. We can tune that later. There's other guides for tuning, but one of the critical loops is the velocity loop. So auto setup, I like to look at current, actual current. Check the velocity parameter. Sometimes this acceleration is a little too high, especially if you have some inertia. So turn that down. Look at actual current. You can set that to 3 Hertz, maybe 500 RPM is a little fast. Try 250. And we hit start, and the commanded or limited will be back and forth. And there's the actual. There's some current to get there, about 440 milliamps. I'm going to try a little higher speed here because I can do it. And you can take a look at the gain here. If the gain is too high, you get a little ringing. When it oscillates, cut it in half. Don't panic. Maybe bolt the motor to the frame there. So it's still a little buzzy with that. There you go. Buzzing stopped. So I'm going to move the velocity loop filter pole out from 200. I'm going to do a single pole, and that should clean things up a little bit too. Got to apply it. I could actually go a little further out with the velocity loop. In this case, it's not a big spindle, so V loop filter. Let's just go to 400 Hertz. 400 Hertz of velocity loop bandwidth. And there. This gain was buzzing last time we looked at it. but the pole was at 200 hertz, and it was a 2-pole, so it's a single pole. 400 hertz allows me to crank up the gain, so move the pole out, the gain can go up a little bit. And let's give it a little integration here. I don't want to go too crazy in case I attach a load. And my command and actual look pretty good. There's a little bit of steady state error, but I don't want to overdo it because I'm going to tune the position loop. So that's yeah, a little bit of current for X cell and D cell. Not bad. We can go back to those slightly bigger parameters and get a little more current for X cell. So 100 milliamps. There we go, about a 150 milliamp. So I got plenty of current headroom there. So now we're going to look at tuning the position loop. So again, 2000 line encoder is 8,000 counts per rev. Just going to do a relative trap move. Auto setup checkbox. Whoop, brought that back. I like to look at channel 3, current actual. I don't want to cloud it up too much, but here's the gains. Here's some trajectory. I don't know if it can do it, but we'll give it a shot. So this is a single rev move, and we'll do a 10 rev move. So little integral pulling it in there. I think I can turn up the integral gain a little bit here. So normally I don't go back and mess with the velocity loop when it's done, but I'm just tweaking the integral here. Oh, that's too much. Maybe 75. So you see I overdid the integral wind up there at the end of the move, so let's bring it back down. There, that looks perfect. So move and settle, and then we're good. If the PP term is too high, you might see a little ring here. The electromechanical time constant there should give us a ring eventually. If you have inertia, this number comes down. No inertia. It's a little buzzy. It's very stiff, but I think it's a little ringy here. So bring it back down to 2,000. Really, before you put a load on, just leave it at 1,000, and it should be fine. But I'm going to show you the feed forward term. If we set it to 0, you get constant error during the move. That's what the feed forward does, is bring that down to 0. So 16,384 is the normal. Yeah, so I like to get this proportional gain down to about 1,000 here. So let's try 1,500. A little bit below it. Okay, it's not too bad. It's not too buzzy. Let's turn the feed forward term back on. If you had dual loop, then you could, double the feedback, but actually you'd use the gain multiplier if you have a dual loop. Just leave this at 16,384. But the idea is the feed forward term reduces the error during the constant velocity portion of the move, so it brings this error back down to 0 while you're moving. You could try to mess with the acceleration feed forward to reduce this error during accel, but I don't like to mess with it too much. It's a little load dependent, and it messes up with my integral too. So here it is. That didn't improve getting the steady state at all. So it depends on what your critical factors are, like scanning maybe. I need to scan while I accelerate. Well, fine, use some acceleration feed forward. But I'm just interested in getting to my position, point-to-point moves, getting to steady state with the least amount of falling error in the quickest time. So I'm going to make a move here that's 3,500 RPM. I'm going to bump into the voltage limit warning. Yes, I've got 26 volts, and my voltage terminal servo is hitting about 20 volts. But we're starting to get into the danger zone here. This is not the voltage at the output. It's the real portion of it, the Q. It doesn't show the imaginary portion, the D. So both those vectors together add to become the bus voltage. So just be careful. If you're hitting a trajectory velocity that's too fast, you'll get a constant voltage warning, and a following error fault. So yeah, it's not designed to go that fast.